4, 5. All right, so we're going to talk about real quick combustion analysis, and then we're going to start in and talk about 4.6, which deals with titrations. So combustion analysis, combustion is where you're burning something in the presence of oxygen. That's what combustion is a reaction in the presence of oxygen. And with this, if we're doing combustion of a hydrocarbon, we're going to end up with CO2 and H2O as our products. So you're going to take O2, and then you're going to have a hydrocarbon. So the hydrocarbon is going to be C with a subscript, hydrogen with a subscript, and then sometimes it also has oxygen with some sort of subscript. Okay, so like if we didn't have the oxygen here, it might be glucose. So glucose in the presence of oxygen, which is cellular respiration, that is a combustion reaction that's happening in your cells even as we speak. All right. So how do we figure out if we are given the amounts of these that are produced? Okay, we can actually take that data, and if we know how many grams of this we started with, we can come up with the empirical formula for this material. Okay, I know it seems like magic, but we can do it. So what you do is you calculate the moles of CO2. Okay, if we know the mass of this and the mass of this, you're going to calculate the moles of H2O. Then you use your percent composition for each of these to multiply by that mass amount of each of these to come up with how much carbon and how much hydrogen you have. And then the difference between that and your starting material and this guy, because that's where your carbon and your hydrogen are over here, the difference between that then is going to be the oxygen in this particular compound. And then you can do your mole ratios and divide by the lowest mole amount, and that gets you to your empirical formula. So let's go through a problem like that. Okay, we have this guy. We have this acid. It's analyzed by combustion. We're starting out with a 0.3 gram sample of this, and it's producing this much CO2 and this much water. Okay, the acid here consisted of carbon, hydrogen, and oxygen. So this is going to be one of these plus oxygen is going to give us CO2 plus H2O. Okay, and I'm just going to kind of keep track of everything. I'm going to put underneath here my grams. So this is 0.03 or 0.3000 grams. My carbon dioxide ended up with 0.579 grams. And here I ended up with 0.142 grams. Okay, everybody cool with that?
There's a spider. Right there. It's hairy.
Thank you, Lippy.
Crawled under there. Where? It's right under the thing.
Lippy, I don't like spiders. I made a noise.
I did make a noise.
Lippy, you are the most powerful person I know.
She did that with no fear whatsoever.
All right, I'm going to take this and I'm going to turn it into moles. So 0.579 divided by, that should be a 9, divided by 44. That's the molar mass for CO2. That's going to give me my moles of CO2. Okay. I'm going to take the 0.142 divided by 18, the molar mass for water, and that's going to give me my moles of water. I'm doing this wrong. I'm being an idiot. I was killing spiders instead of paying attention. Hope you have a good eraser.
We're backtracking. Today's been a rough day for us.
All right. My carbon here, this is 12, and I'm going to divide that by 44. That's going to give me my percent carbon in that compound. This is going to be 32 divided by 44. That's going to give me my percent oxygen in that compound. So this ends up being, and I'm just going to leave it as 0.273 so that I don't end up having to divide it by 100 for my next step. And this will be 0.421. Okay, that's my parts of these. Good?
What are you getting? 12 and 44.
This is 12 off the periodic table. This is 32 off the periodic table, 2 oxygens. 16 plus 16 is 32. And then if I add 12 and 32 together, that's 44. Everybody with me so far? Do you need to move seats? These are my percent. So this is, the carbon is 27.3% of this mass. And the oxygen is going to be 42. That doesn't add up. 72. God, I'm looking at the wrong spot. Boy, am I off today, guys. I am so sorry. 0.727. Better? Okay. So this is 72. The reason why I knew right away that that was wrong, because this should add up to 1. Okay. So 72%, 73% of this mass is going to be the oxygen. So I'm going to multiply these by that mass amount. And then that's going to give me the mass of the carbon and the mass of the oxygen. It was given in the problem right here. All right, 0.157 grams here. And now is my time for 0.421 to come in. It's 0.421 grams of the oxygen. I'm going to do the same thing for this guy, for the water. So water, my hydrogen and my oxygen. My hydrogen is going to be 2/18. That's 0.111. My oxygen is going to be 16/18, which ends up being 0.889. Okay, then I multiply that times the mass of the water. And I end up with 0.0158 here and 0.126. This is going to be my grams of oxygen in that water. This is going to be my grams of hydrogen in that water. This is going to be my grams of oxygen and my grams of carbon. So if we follow through our conservation of mass, the grams of carbon in this material has to be this amount. The grams of hydrogen in this material has to be this amount. Okay, so that's going to be my carbon is 0.157 grams of carbon. My hydrogen is going to be 0.0158 8 grams of hydrogen. I've got to figure out my grams of oxygen. And it's not going to be adding these two up. Why? Because we got oxygen right here. So how do I figure out my grams of oxygen in this material?
Would it just be the 0.126?
No, because you don't know how much of that was in here. We don't know what this is.
Add and divide.
Nope. I know my carbon. I know my hydrogen.
Oh, add those together to see how much you have left over.
Right. So you know how much this is. Okay. So if I know how much the whole thing is, and I've got this part and this part, the difference then is whatever is left. That is your oxygen. If it contains 3 parts and you know 2 of them and the whole, you should be able to figure out that third part. Yes? Okay. So that's what I did here. And my oxygen then, if I add these 2 up and then subtract from 0.3, it ends up being 0.126. Okay. Then I'm going to turn these, and I'm going to switch pen colors so you can see it a little bit better. I'm going to turn these into moles. Yep. So I'm going to divide this by 12, divide this by 1, and divide this by 16. So this ends up being 0.0158. I can do that in my head, at least. This guy ends up being 0.0132. And this guy ends up being 0.00790. All right, what do I do next? Right, find the lowest mole value and divide everything by that. That's okay. I want to remember to go and clean it up later. So that's why I left it kind of out in the middle there. So I'm going to divide everything by the lowest mole amount. So this guy will end up being 1. Yep. This guy will end up being 2. And this guy ends up being 1.66 repeating. Can I have a formula? Exactly. I can't have a formula that looks like this. Okay, you have to have whole numbers for your subscripts. So what do I multiply everything by? I'm going to multiply everything by 3. Not loud enough. So this ends up being 5. This ends up being 6. And this ends up being 3. So my formula, or my answer, ends up being C5H6O3. So we went through all of that to get to the answer.
3 numbers.
Yep.
There's so many.
Yes.
You kind of lost me when you started dividing by 12, by 1, and by 2.
I'm getting these into molar amounts here. So I'm taking these grams that we got from this previous problem. I'm dividing by the molar mass off the periodic table. That then gets me into moles. That's the blue numbers here. After that, then you find whichever mole value is the least and you divide everything by that. So this ended up being 1.66. This ended up being 2, and this was 1. Because this wasn't a nice whole number, we have to then find a number that we can, the lowest number that we can multiply it by to make it a whole number. So in that case, it's 3. So this ended up being a 5, a 6, and a 3.
So how do you know that it's 3?
Here?
Yeah.
Because that's the smallest number that I can take that'll make this a whole number. So if it was like 1.5 instead, I'd multiply it by 2.
what if it was like 1.8?
Looks like 5 works. Yeah. Okay, good. All right, moving on to hydrates then. So I don't remember if we've talked about hydrates in here this year or not, so I apologize if I end up doing this again. But a hydrate is kind of like a molecule. It's a molecule, okay? And then it's almost like you've got some water that's kind of been like Velcroed onto. It's not Velcro, of course, okay? But it's stuck on there, okay? And what you can do with this is you can actually apply heat to it, okay? And the heat will drive the water off into the air. And what's left behind then is the anhydrate. And if you took regular, or if you took pre-AP with me, we did lab like this, where we measured some of this stuff, okay? And what you can do then is you can take the mass of this material, subtract it with what you started with, and that's going to give you the mass of the water that you drove off, okay? And then you can put it into mole ratios like we did in the previous problem and come up and figure out how many waters were stuck on here. So for example, this one, CuSO4, has 5. And they call this pentahydrate. Penta means 5. This is the way that would be written. So the stuff that you were working with yesterday was this stuff. So there was 5 waters that were on there. And that's why you had to use that when you were doing your molar mass. You had to include that water in your calculations for the material that you had on your balance to figure out how many grams or how many moles you started with. Because that water was on there and we didn't drive that off. We just mixed that together. So that water was stuck in with that CuSO4. The 5 waters, yep. Yeah, you have to include, whenever you're working with your calculations on that, you have to take the mass of this and the mass of these 5 here. So 5 times 18, whatever that is, added together gives you the molar mass of this material. And there's certain materials that lend themselves to this, but they end up having different amounts of water that can kind of get attached to it. So for example, the problem that we're looking at here is we're trying to figure out what this number is, and we can analyze this material to figure that out. So what we did here was we started with 11.7 grams, and that's the COCl2.H2O. We don't know what this is. We're trying to figure out this question mark here, okay? We then heat it, and once we heat it, it ends up being 6.410 grams. That's just the COCl2, okay? We can subtract then. When we subtract, what is that material down here going to be?
H2O.
Yep, this is going to be your grams of H2O then. So when we subtract that, it ends up being 5.32. Okay. So then I'm going to take this guy, the 6.410. I'm going to divide it by the molar mass of copper chloride, which is 129.93. I'm going to take my water and divide by 18. And when I do that, this guy comes out to be 0.0493. My water comes out to be 0.296. Then I divide by the lowest mole amount. Now, when you're talking hydrates, your water moles should be higher than or equal to this. This should always be your lowest mole amount. Because if you think about how these form, you've got your molecule and you're trying to figure out how many waters are around the thing. So this is always going to be set in a 1 to something ratio, but this is going to always be your 1. Does that make sense? Yeah. So because of that, this has to be your lowest. Now, if it's a 1-to-1 ratio, then these moles would be equal to each other. If they're not in a 1-to-1 ratio, this number has to be your bigger mole amount. Okay? So you're always going to be dividing, in this case, by whatever your anhydrates moles are. If this mole amount isn't equal to or less than this amount, you goofed something. Something is terribly wrong. All right, so I'm going to divide this by 0.0493. When I do that, I end up with a 6. So we wanted to know x equals 6. So the formula for this would be COCl2.6 H2O. We would call that cobalt chloride hexahydrate. Okay, everybody cool with that? All right, now we're going into your packet. We are going to switch into titrations.
Is there any homework for that other, well, besides the lab? I was talking about like for this. Yeah, that was just supposed to go over enough.
Yeah, it was supposed to be part of your 4 or 5 notes.
Okay.
I just goofed and didn't get it in there. All right. For this unit, you can use this formula to kind of help you out. Okay? Where you have moles times molarity of your acid times the volume of your acid will equal your moles of your base times the molarity of your base times your volume. So just kind of keep that in mind. Because when you're doing a neutralization reaction, you're going to end up equaling each other at some point. Okay? So titration is an analytical lab technique. We're going to use burettes. So you guys are going to start using burettes coming up in the next few days. I think the lab is next week, if I'm not mistaken. You're going to be using, or maybe it's the week before Thanksgiving, which may be next week. I don't even know anymore. My timeline's so off. Using the balanced equation, then you can figure out how many moles of your titrant we need to get to this equivalency point. So the equivalency point is when the moles of the titrant, so the stuff that you're titrating in that's in your burette, that's called your titrant, is equal to the moles of the analyte. So that's the stuff that's going to be in your flask. So you're going to have this set up. So you're going to have a flask here, usually an Erlenmeyer flask. Then positioned on a stand, you're going to have one of these super long tubes called a burette. Okay. And this stuff here that's in the burette is called your titrant. This is called your analyte because you're analyzing this material and you're trying to figure out its composition. So the equivalency point then is where the moles of this material are equal to the moles of this material. And you'll have some sort of endpoint that'll show you that. If you remember back in honors chem, we did a strong acid, strong base titration. And your endpoint, you wanted just the faintest pink color.
Yeah, I know, you guys got it right away.
Okay. And it's a very kind of touchy technique that you have to kind of work with. Now, The beauty with the lab that you did when you did this in honors chem was if you overshot the end point, you could go back and you could recover. The lab that we're doing on this now, there is no recovery. You overshoot the end point, there is no recovering. You got to start over. Okay? So you need to be exceedingly precise with you need to be exceedingly precise and really good with your technique in titrating this material in, because there is no recovering if you screw it up. If you go past that endpoint, you are done. Okay? All right. So there are common types of titrations. The one that you would have done in honors chem or pre-AP chem was an acid-base titration. This is where you're adding acid or base into acid. So you were adding base into an acid, and you're trying to get the equivalent point. In that case, it was a strong acid, strong base. The equivalent point would have been a pH of 7. Okay? So you're trying to equal your hydrogen ions will equal your OH ions when that happens. Redox titrations, then, you're going to have a color change. And that's what you're looking for with this lab. You're going to be doing what's called a redox titration. And we're going to get into redox in the next day or so. So redox titration, you're looking for a color change, and that's going to tell you when that oxidation state of the metal has changed, and all of it's changed over. And then there's also precipitation titrations. We don't end up doing those in here, but you can look for some sort of precipitate that's occurred at that point. All right, so what do you need for this? You're going to need a stand. You're going to need one of these burette holders. You're going to need a burette, and then you need a flask here. And then typically you'll also have a lot of times like a waste beaker that you use to be able to drain this or to get it started. You need to make sure that there's no air bubbles down in the tip here. If there is, you kind of got to lightly flick it. Remember, you've got what's called a stopcock here. The stopcock is what's going to control the flow of your titrate down into your analyte. And volumetric flasks, we can oftentimes, when we did this in pre-AP, we just used another burette for this instead of a volumetric pipette. Then sometimes you're going to have a balance because you're actually adding a powder into this flask and then mixing it with a couple other things. We're not going to have an acid-based indicator or a pH because we're not doing acid or base titrations. So data that you need to keep recorded, you need the molarity of the titrant. You need the initial volume of that, the final volume of that, and then the volume or mass, in this case, the mass of this analyte. So if we're doing an acid-base titration, you can sometimes use a pH monitor to show you when, and that we will do one of these when we get into Unit 8. And you can actually have this hooked up to your vernier lab probe, the pH meter, and you're watching for when this guy is a straight line. When that guy is a straight line, if you follow that down to the volume that you've dispensed, that's going to tell you where your equivalence point was. If you're looking in terms of pH, if you take this and you divide this up equally, then that's going to tell you where your equivalence point was with in terms of pH. So like I said, you drop the line down here. That's going to give you your volume for that. All right, here we go. You ready? So here's an acid base. Stuff there. All right, here we go. So for this guy, we've got hydrochloric acid. We're dispensing that into an Erlenmeyer flask, and then they're adding 25 mils of water in, and then 3 drops of phenolphthalein. That is just going to indicate by turning pink when your equivalence point is between the hydrochloric and the sodium hydroxide. Okay, so at this point we have 10 mils of acid and we have 25 mils of water that have been added. They've got our phenolphthalein in there. Then we are going to take 0.4 molar sodium hydroxide. They're putting that in the burette. Their initial reading is this amount on the burette. And then they're adding it in 1 mil increments until the pink color briefly appears and disappears. And then once that starts happening, you want to go much slower. Okay? So at that point, they're going drop by drop. And when the pink color lingers for 30 seconds, you stop. The final volume reading then was this amount. So we want to figure out the molarity of the HCl. So the first thing we're going to do is we're going to subtract these values. Okay? So by subtracting these values, that's going to tell me how much NaOH I ended up using. So you can probably do that in your head. 17.99 mils of NaOH were used. And if I multiply that times my molarity, that's going to give me my moles of NaOH. So if I look at my equation and what's going on here, this is my balanced equation. So that means these are all ones, everything's a 1. That means that if I had this many moles of NaOH used, how many moles of HCl would I have had to use? The same, okay? So 0.007196 moles of HCl were used. And I know that I used how many mils of hydrochloric? 10, so that's 0.010, liters of HCl. So all I have to do is subtract, and that's going to give me a molarity of 0.720 molar HCl. Did I say multiply? I meant divide. I'm sorry. I don't know. I said subtract. Divide it. Do as I write, not as I say, apparently. All right. So the next one here, and this is actually the lab that we're going to be doing. Okay. So we've got sodium, we've got hydrogen peroxide, we've got potassium permanganate. We're going to have it in an acidic solution. We've got this reaction going on, and they want to calculate the amount of hydrogen peroxide in that sample if we required 15.1 mils of this guy. So this guy right here is this right here. So figure out your moles of that. From there, you should be able to figure out your moles of this. And then you've got your volume of that. So then you should be able to figure out your molarity. No, grams. They wanted to know grams. I'm sorry. So if you figure out moles of that, all you have to do is do grams. You don't even have to figure out molarity. So yeah, so figure out your grams. So take a minute to do that while I pick up my mess from earlier over here. You should have your calculator out. You should be turning this into moles. Step 1, turn this into moles. You have molarity, you have volume, you have the equation, M equals moles over liters. Sig figs, I would use 3. 3 here. Where's my pen? Where did my pen go? I'd blast it. Right, but this is 3 sig figs and this is 3 sig figs. So because of that, that's going to limit you to 3 sig figs, even though that's 4. Here's my pen. All right, so if you multiply these two things together, right, I have to turn this into liters and then multiply them together. I'm going to end up with 3.775 times 10 to the minus 4 moles. And that's going to be my MnO4 minus. So if I take that up into my cloud, I'm going to do what to this number? Up into the cloud, what do we do? Okay, so I'm going to divide by 2, and then coming back down out of the cloud, I'm going to take that same number and I'm going to multiply it by 5. So if I take this and I divide by 2 and I multiply by 5, that's going to give me my moles of H2O2. And then what am I going to do with that value? Multiply it by
18.
Nope, it's H2O2, so 34, and that's going to give me my grams of H2O2. It was not bad at all.
Why does it say KMnO4?
Because it's potassium permanganate, but if we were to do this, we could do this as a regular equation. This is a net ionic equation.
Oh.
So the potassium, remember potassium is always going to be soluble. So when this is in an aqueous situation, that potassium is going to remain soluble. Okay.
It doesn't like signify that it's a net ionic equation.
Well, it has these ions, so it kind of does. All right. So tonight your homework is 7-6 and your lab. I will see you tomorrow.
When's the lab due?